The time has come to actually start solving some differential equations. So to begin with, let's try solving this differential equation. dy dx equals x times y. Now, one thing that you might try is, since we're trying to find the unknown function y, well, look, on the left-hand side is the derivative of y, so why don't we just integrate both sides? That would give us the integral of dy dx equals the integral of x times y. But actually, what I've written here doesn't really make sense. If you're integrating, you have to have some differential, some d of something, to make the integral work. In other words, you have to decide what variable you're integrating with respect to. And we have two choices, x or y. And if we try to integrate with respect to either one of them, we actually end up with the same problem. So on the left-hand side, if we integrate with respect to x, we can do this integral. So the integral of dy dx with respect to x is just y. But on the right-hand side, we need to integrate x times y with respect to x. But remember, y is actually an unknown function of x. How are we going to be able to do this integral when we don't actually know what the function inside the integral is? So this integral on the right-hand side, we're just not going to be able to do it. And so that didn't really work out. This way of trying to solve the differential equation just didn't work. And you can see the problem here is, on this right-hand side, we have a mix of variables. We have both x's and y's showing up in this integrand. And that's really what causes this whole problem. So that gives me an idea. Why don't we take this differential equation and try to separate all of the x's from all of the y's? In other words, get all of the y's on one side of the equation and all of the x's on the other side of the equation. So to start with, I guess we could multiply both sides by 1 over y, just to get this y off of the right-hand side. So now we have 1 over y times dy dx equals x. And we don't actually have the x's and y's separated yet because there's still a dx on the left. Now, one of the great things about this d notation for derivatives is the ratio dy dx is a derivative, but we can actually treat the dy and the dx separately as differentials. And so we can actually multiply both sides of this equation by dx, and the differential on the left, dx, cancels the one right there, and we get 1 over y times dy equals x times dx. And now we can integrate both sides. And the way we have it set up, we don't have to decide what we're integrating with respect to on each side, because the differentials are already there. So on the left, we're integrating with respect to y, and on the right-hand side, we're integrating with respect to x. So we can actually do these integrals, right? In both of these integrals, there's only a single variable. There's not a mix of variables like we had before. So we can actually compute these integrals. On the left-hand side, integral of 1 over y is the natural log of y. On the right-hand side, the integral of x is 1/2 x squared. Now these are both indefinite integrals, so we have to put a constant of integration somewhere, either on the left or the right, and I'm going to put it on the right-hand side, so let's put a plus c right here. Remember, we were trying to solve for y, so all we have to do now is solve this algebraic equation for y. We can just exponentiate on both sides, right? Use both sides as an exponent on e. On the left-hand side, exponentiation base e and natural log base e undo each other, and we're just left with y. And on the right-hand side, we get e to the 1/2 x squared plus a constant. Now this is almost good enough. It's sort of a little weird to have this constant in the exponent. So what we can do is just use the laws of exponents to split this up. This is e to the 1/2 x squared times e to the c, and then we can just define a new constant a to be e to the c, and we get y equals e to the c, which is a, times e to the 1/2 x squared. And we've solved the differential equation. I won't plug this back into the original equation to check, but if you do plug this into the original equation, it really does solve that equation. So, and notice that we get a one-parameter family of solutions to this differential equation sort of naturally as a consequence of the constant of integration, c. So this little trick that we had of separating the variables actually worked. So let's ask ourselves, this trick did work, but what was it about the original equation that made this work? Well, what made it work is we were able to get all the y's over here, and the dx we were able to get over there. But, I mean, why is it that we were able to get the y to the left? If you think about it, it's because the right-hand side of this differential equation was x times y. It's that times that was important. If this were a plus or a minus, it actually wouldn't work. It has to be a times here. So in general, for this trick of separating the variables to work, we need the right-hand side of our equation to be a function of x times a function of y. And these functions can be anything as long as they're multiplied, right? Okay, if we have a differential equation like this, in principle, we should be able to use the same trick to solve this differential equation. So let's divide both sides by the function of y, like this. So on the right-hand side, the g of y cancels. So now we get 1 over g of y times dy dx equals f of x. And now we're going to multiply both sides by dx, just like we did before. And that makes the dx on the left simplify away. So now we have 1 over g of y dy equals f of x dx. And then we'll just integrate both sides. Now we can't actually take this any further because we don't know what these functions are, so we can't actually perform these integrals. But from this point onwards, what we would do next is calculate the integrals. And as we calculate the integrals, we need to remember to add our constant of integration somewhere when we do those integrals. And then once we've calculated the integrals, we'll have an equation with y in it, and we can just solve for y. If possible, if you aren't able to solve for y, you'll end up with an implicit solution. But if you can solve for y to get an explicit solution, then you should do that. So this sort of equation, this sort of differential equation that starts out with a product of a function of x and a function of y, this is called a separable equation because you can separate the variables. So if we have a separable first order equation, we have a trick that will let us solve this differential equation as long as you can do these integrals. It turns out that's often the tricky part because, some integrals are really hard. But as long as you can do the integrals and solve for y, then you can get a solution to a separable equation.